right, so next section we are going to look at is 3.3. It's on the factor theorem, and we're also going to be looking at long division. So the goal in this section is to start to learn how to factor things that are higher than an exponent of 2, okay, and solve equations that are higher than quadratic, okay, like cubic or quartic. When we get into those equations, we need to have some nice things work out, or we're not going to be able to do them. Okay, the ultimate goal is to take every problem that's not a quadratic and turn it into a quadratic. Because if we can reduce a problem down to a quadratic, we can always solve quadratics. Okay, we've got the quadratic formula. But the goal is, can we get to a quadratic from what they give us to start? So just a couple reminders what zeros and roots are. Remember, those are numbers that if you plug them in for x, you will get 0 for y. Okay. You can call that number a root, or you can call it a 0. And you can write down a sentence, and you can word it two ways. Okay? You can have a sentence and what's called its converse. So if you find a number that's a root, then if you plug it into the equation, you'll get 0. Or you can read it the other way. If you have a number that you plug into an equation and you know it gives you 0, then that number is a root. So this is an if-then statement, but that means you can read it forward and backwards. IFF. So just a short way of writing if A then B, if B then A. A statement and its converse, all is one sentence. So we're going to look at using long division to help us find roots of polynomials. So let's think about when you do regular division. Right? Forget, we're not going to do long division with a polynomial just yet. But just do it with a regular number. So if I wanted you to factor the number 12, okay, and I tell you that 3 is one of the factors, how would you get the other factor? Yeah.
Divide 12 by 3.
Divide 12 by 3. Okay? If you know that something is a factor, that basically means that 3 times something will give you that number. Okay? How do you solve for something? Well, divide 12 by 3. And that gives you 4. So 4 is the other factor. And that's going to work with polynomials as well. If you don't know how to factor something, but I tell you like x plus 3 is one of the factors, you can find the other one just like I did here. Divide what you're trying to factor by the known factor, and that'll give you the other one. Now, what happens when you divide a number by a factor of it? You always get a remainder of what? Yeah. 0. Okay, so if you divide a number by a factor of it, you will always get a remainder of 0. If you divide a number by a number and the remainder doesn't come out to 0, then what you divided by is not a factor. Right? 12 divided by 5, you get a remainder of 2. That's because 5 is not a factor of 12. So getting remainders of 0 is going to be very important. That's something we're going to focus on in a little bit. So if we can figure out quick ways to divide things and look at the remainder, then we can quickly tell if something is a factor or not. Because division with a remainder of 0 proves that the thing you divided by is a factor. Okay. So we can get remainders by doing long division, but there's other ways we can get remainders as well. Okay. Sometimes. Depends on the complexity of the problem. So we're going to first look at how to get remainders doing long division. Then we're going to look at a faster way to get remainders that works some of the time. So that's what I said to you guys earlier. If you divide two numbers and get a remainder of 0, then what you divided by is a factor. Okay, so why would we want to factor things? Well, if you had something like that, okay, somebody may have a hard time trying to figure out what you could plug in for x to make it 0. But if you factor it as x plus 1, x plus 2, then it's very easy to see negative 1, negative 2. Those are the two numbers you can plug in. Okay, so that's why we're going to try to factor things, so that we can find the roots of polynomials. So what we'll do now is we're going to go through the long division process for a polynomial. What I'll do is put this side by side with an example. So we'll look at a step, then we'll do the step. Okay, so the first step when you are doing a long division problem is leave yourself plenty of space, because you'll need a lot of room down and to the right. That's kind of how these problems go. So you don't want to start a long division problem on the right edge of the page. Once we put it in the right spot, we've got to make sure we are not missing any terms on the inside. If we are, we need to put placeholders in so we can line things up nicely in columns. You need a column for every single exponent from the highest to the lowest. Am I missing any terms in my dividend? Yeah?
X squared.
I'm missing the x squared, so I got to fill that in. So let's do x minus 3 divided into x cubed. Okay, I'll put 0x squared. That's going to be a placeholder for my x squared column. Minus 8x plus 3. All right, so that's step 1. Now step 2. You're going to divide the first term on the outside into the first term on the inside. Inside is the dividend, outside is the divisor. So we're going to divide the first term here into the first term there. So off to the side, if you want to kind of think about what you're doing x cubed divided by x. And what's x cubed divided by x? Yeah?
X squared.
X squared. You can put that anywhere you want up above. We don't have to line up the quotient, which is the answer up top, with anything. Just put the x squared anywhere you want up above the line. Okay, so now we're going to multiply the answer that we just got in step 2 by each term on the outside, and now we have to put things in the correct column. Okay, so let's multiply this back out. What's x squared times x? Yeah?
X to the third.
X to the third. Put that in the x to the third column. And what's x squared times negative 3? Well, Raj?
X squared.
Yep, negative 3x squared. So we're multiplying that back. Okay, next step. We're going to subtract the columns that we just did in step 3. Okay, so we're going to subtract the columns we just did in step 3. So the way I do that is this. Put a subtraction sign in front of the whole thing. And now we'll subtract. Okay. What's x cubed minus x cubed? Let's.
Would it just be 0?
Yep, so 0, that's gone. Something should always cancel out at this step. If it doesn't, then you made a mistake. And what's 0x squared minus negative 3x squared? Yeah.
Would it just be negative 3x squared? Because the 0 just removes the x squared. Oh wait, no, it would be positive, right?
Positive 3x squared.
Because
Yeah.
negative 1.
Yeah. So positive 3x squared. And now what's the next thing you do when you're doing long division at this step? Even with just regular numbers. Yeah?
Fill in the rest of the numbers at the top. Put it, it's like 3x squared minus 8x plus 2.
Yeah, so we'll bring down, you don't have to fill them all in right now if you don't want to, but you at least got to fill in the next one. So we're going to bring down the next term, and we're going to keep repeating this process. Notice at this step, when I bring down the 8x, or negative 8x, the exponent here now is a 2. It started out as an exponent of a 3. Okay, it went down 1. Every time you do a round of long division, that exponent is going to go down. You have to keep going until the exponent here is smaller than the exponent there. Okay? Exponent on the outside is a 1. Exponent on the inside is a 2. So until the number on the inside is smaller than the one on the outside, we're not done. Okay? So now let's do it again. So now divide 3x squared by x. What's 3x squared divided by x? Yep.
3x.
3x. Put that there. Multiply it back out. 3x times x gives me how much? Marcelo?
Wait, what?
So 3x times x.
3x squared.
And what else will go next to it?
Negative 9x.
Perfect. 3x times negative 3 is negative 9x. And what are we going to do with these columns now? Yeah.
Would subtract.
Yep, we're going to subtract them. So go like this. 3x squared minus 3x squared, that's gone. What's negative 8x minus negative 9x? Yeah, Raj? X, good. Okay, exponent on x is a 1 here. Exponent on x there is also a 1. We got to keep going. But this will be the last round because then the exponent on the inside will be smaller. All right, so bring down your 3. And now do x divided by x. How much does that give me? Yeah, 1. Now multiply it back out. 1 times x, 1 times negative 3, and subtract. What's my remainder going to be? Yeah? 6. Okay, so a couple different ways we can write the answer. The quotient to this division problem is x squared plus 3x plus 1. The remainder to the problem is 6. Okay, so that's one way you can write your answer. Now, you can also write it the way you would do it with long division with numbers. Okay, so let's say we had 13 divided by 5. What's the quotient there? Yeah? 2. And what's the remainder? 3. So another way that you can write your answer when you do long division is quotient plus remainder over your original denominator. This is 2 plus 3/5, or as a mixed number, it would be 2 and 3/5. So I want to do that same concept over there. Quotient plus remainder over the original denominator. Okay, let's do that. Bless you. Bless you. So quotient, x squared plus 3x plus 1, plus my remainder, divided by my original denominator, which was x minus 3. That's another way you can write your answer. And the nice thing about the second way is I can check that. Okay, I can type in the original problem, I can type in my final answer, and when I graph them, they should look identical. So let's try it. Let's type in x squared plus 3x plus 1 plus, and you're going to need parentheses here, 6 divided by, parenthesis again, x minus 3, close the denominator, close the entire fraction that you're adding. Okay, so that's our answer. Now let's type in what the original question was. So it was x cubed minus 8x plus 3. X cubed minus 8x plus 3 divided by x minus 3. You don't have to fill in missing terms in the numerator because we're not doing long division here. We're just graphing it. Let's do zoom 6. Okay. So that's our answer to the problem. And here's the original question that they gave us. So the two came out exactly the same, which means we did it right. Now, I don't want to get into it too much, but has anybody noticed there's almost like a shape here that's in this graph, but it's not quite this shape. Anybody notice a shape there that starts to appear, but then it changes a little bit? Yeah?
Parabola.
It almost starts to be a parabola. And it actually is more of a parabola. If you set your y-max higher, you will see another part to it. So here's the part that looks like a parabola. And did I go high enough to see the other part? No, I guess I didn't. But eventually, if you did go high enough, you would see the parabola start to continue on the other side. Let's try it one more time. So there's the first part of it. There it is. If you zoom out enough, you will see kind of a parabola shape overall to this graph. But it doesn't connect because 3 is not in the domain. You'd be dividing by 0. So it is a parabola, but there's a break right in the middle of it because of the divide by 0. Yeah?
Right over the valley.
Yeah. Okay. Any questions on not so much the graph, but how we got our answer? Okay. So let's try this one. Okay, are there any terms missing in the inside that I need to write down? You good, Marcelo? No. Nope, they already did them for us. So we got everything lined up, so that's good. So first thing we're going to do is 2x to the 4th divided by 2x squared. What's that going to give me? Yep.
X squared.
Yeah, it's going to give me x squared. Now let's multiply that back out. Jaden, what do you get when you multiply that back out to each term?
2x to the 4th
Yep.
plus x cubed
Plus x cubed
plus x squared.
plus x squared. Okay, so we got everything multiplied back out. And Annalise, what am I going to do with all three of those columns? I'm going to subtract. That's gone. Negative x cubed minus x cubed. Negative 2x cubed. And 0 minus x squared is negative x squared. You can bring down the next term, but it's just 0. So 0x. And now do the division again. Negative 2x cubed divided by 2x squared. What does that give me? Yep.
Negative x.
Negative x. Okay, and now multiply that back out. Jackson, what do you get when you multiply that back out?
Negative 2x. No, 2x.
Negative 2x to the,
Negative 2x to the third.
yep, negative 2x to the third. Good. All right, my next term.
Minus x squared.
Yep, so we got negative x squared, good. And the last one,
Minus x.
minus x, perfect. Okay, and we're going to subtract all those. Negative 2x cubed minus 2x cubed. That's gone. Negative x squared minus x squared. That's gone. Okay, when two things cancel at the same time, that's good because now it just eliminated having to do this an extra time. 0x minus x leaves me with x. What's the degree on the x on the inside? Yep, 1. What was the degree of what was on the outside? Yep,
It was square root of 2.
2. We're done now. We can't do any more because you can't divide 2x squared into the x, right? Because the exponent on the x is smaller. So that, just bring down your 2. That's your remainder. Okay, so quotient in this case is x squared minus x. Remainder, x minus 2. Any question on that? So now, if I asked you to factor this problem right here, would you say that this is a factor of that? No? How come? Because there's a remainder. We didn't get a remainder of 0. Same thing here. If you were trying to factor this, that is not one of the factors. And I know that because I got a remainder of 6. If something has a remainder when you divide it, it's not a factor. All right, so let's look at this. And I think it'll help if you think about it in terms of numbers. So let's say, let me use, what did I use before? 10 and 5 and 13 or something like that? Let's do those numbers. So let's say, just to keep it simple, let's say f of x is the number 13 and h of x is the number 5. If you start with those two numbers, then there will be a quotient, if you figure it out correctly, and a remainder, if you figure that out correctly, that satisfy this equation. Let's check it. 13 equals 5 times your quotient plus your remainder. Is that true? Okay. What are you actually doing right here? You learn about that when you do long division. When you multiply your denominator times your quotient and add your remainder and see if you get the original number that was in the top of your fraction. What is this actually doing for you? Well, it's one way to see if what? Yeah.
Your answer's right.
Yeah, it's how you check your answer in long division. You always take your denominator times your quotient and add your remainder. If that comes out to the number you started with in the top, then you did it right. If that doesn't come out, then you did it wrong. Okay, so this is how you check your answer when you do long division. Denominator times quotient plus remainder. So remember that when we are done, okay, when you get to the end of a problem, we know that one of two things is going to happen. Either the degree on your remainder is smaller than the degree on your divisor, and that's what happened in the last two. Degree on the remainder here is a 1. The degree on the divisor here is a 2. That also happened here. Degree on the divisor is a 1. What's the degree on that? Yeah?
0.
0. That's a degree 0. That's a constant. So the degree on the remainder always comes out smaller than the degree on the divisor. Or you end up with a remainder of 0. That can happen as well. So what does that mean if we always forget what's in the top? But let's say you divide by something linear in the bottom. X plus or minus a number. If you divide by something linear, what kind of remainder are you always going to get based on this fact? Yeah?
Well, it's going to be less than the divisor, but it's not going to be 0.
Okay, so what kind of remainder would it be?
Positive.
We don't know if it's going to be positive or negative. That we don't know. Could come out either. We don't know if it's a fraction or not a fraction. We don't know anything like that. But we do know something. If you divide by something linear, you will always get a certain kind of remainder based on that fact. Yeah?
Constant.
You will always get a constant. Okay? Anytime you divide by something of the form x plus or minus a number, you are dividing by something linear. Your remainder will always be a degree lower. Well, the only thing lower than a degree 1 is a degree 0, a constant. Okay? So that's a nice trick to keep in mind. Okay? If we divide by something linear, the remainder will always be a constant. Okay, so what I want to do is I want to apply this formula we just had right here. But instead of just dividing by anything, which is this formula works for anything, I want to make this formula more specific. I want to make it specific to dividing by something linear. Okay? So I'm going to change this to look more like this. I'm going to force h of x to be something linear, like x minus a number. Okay? And that's how I'm going to write it. Okay, so all I've done here is f of x can be anything you want. That's just a generic polynomial. But now I'm going to force us to divide by something linear. Okay? It has to be x minus a number. And technically it could be x minus a minus number, so that would be positive. But I want you to think of it as you're dividing by x minus a number. So what does that formula turn into? Well, you still have the f of x on the left. But instead of h of x now, I want you to write what we are dividing by specifically. That's your denominator times your quotient plus your remainder. Right, so that formula is the one I just did up above, but I filled in something very specific for my denominator. X minus a number. Now, I want to look at what happens if I plug in a certain number right here for x. I can make something very special happen if I plug in a certain number for x. Does anybody have an idea what you could plug in for x? And if you do this, something very special is going to happen to what's inside this box. Yeah?
Would it be a 0?
It's not a specific number. It varies from problem to problem. So you're going to have to describe it to me in terms of a variable. Yeah? C, yes. If you plug in the number that's right there in your division problem into that formula, if you fill in a C, what would happen to what's in that box?
function of x would just be equal to the constant.
And what is the constant?
R.
R, and what does R stand for?
Remainder.
Remainder, yeah. Right. If we plug in c for x, change all the x's to c's. F of c, c minus c, q of c plus r. This whole part disappears. And all you're left with inside that box is the r. What's the r? It's the remainder. So by plugging in the number after the minus sign, we can very quickly figure out the remainder of a division problem if you're dividing by something of the form x minus a number. If you're dividing by something like x squared minus a number, no, that doesn't work. It has to be x minus a number. So we can quickly get the remainder. Why would we want to quickly get the remainder? What would that do for me? Yeah?
See if it's a factor.
To see if something is a factor. Exactly. Okay, so this is called the remainder theorem. If you divide, the top can be anything. There's no restriction on that. Anything you want in the top. But as long as you divide by something that's x minus a number in the bottom, you can take that number that's after the minus sign. Don't take the minus sign with it. Just the number after the minus sign. Fill that number in to the formula that's in the top of your fraction, and you can quickly find your remainder. Okay, so f of x is what's in the top. So you're going to take the number after the minus sign and fill it into the top. Now, we've already done a problem where we divided by something linear. Let's go back and do it again. But this time, we're just going to find the remainder using this trick. This one. We divided by something of the form x minus c. What's my c in this case? Yeah?
-3.
Not -3. Yep.
Already.
3, right? It's just what I circled, just what comes after the minus sign. That's the c. So in this case, that's the c. So plug in 3 for x in the, that's like the top of your fraction right there, and watch what happens. So I'm going to change all the x's to 3's. 3 cubed minus 8 times 3 plus 3. What's 3 cubed? Yeah?
27.
27 minus 24 plus 3. What's 27 minus 24? Yeah? 3. And 3 plus 3 gives me 6. What did we get for a remainder when we did this problem? We got 6. Yeah. So that's a very quick way you can find the remainder. It doesn't give you the quotient. If you want the quotient, that's, well, then you're going to do long division. But it does give you a quick way to find the remainder. Just take the number after the minus sign and plug it in. So now I could give you some like insanely long numerator, 8x to the 57th minus 4x to the 23rd minus 6x cubed. And I could ask you, what's the remainder when you do that problem? I wouldn't ask you for the quotient. Because remember, if you're doing long division, you've got to fill in zeros for every term you're missing. So you have to have every single column from the 57th power all the way down to your constant. And there's a lot you're missing. So to do long division to find the remainder, that's just not practical. But to take the number 4 and just fill it in everywhere you have an x, that's easy enough. I mean, you're going to get some big numbers, but you can do that on a calculator. So any question on the advantage of the remainder theorem? Okay, so now we're going to just find a couple remainders. Okay, 2 different problems. I'm going to reuse the same numerator in each problem, but the first time I'm going to divide by h of x, and then the second time separate problem, I'll divide by g of x. Okay. So let's say that let's do f of x divided by h of x first. Let's do this one. And if I do f of x divided by h of x, am I dividing by something that I can use the remainder theorem on? That's the first step. Marcelo?
Yeah.
Yes, I am. Yep. Now I have to decide what the number is that I'm going to plug into the top. What's the number that I would plug in to get the remainder? Yep.
3.
Yeah. I would take the 3 and fill it in. Okay, so when we do this problem, the remainder will be 27 minus 3 squared is 9 times 2 is 18 plus 3 minus 5. Okay, 27 minus 18 is going to give me how much? 9. And 9 plus 3?
12.
12. And 12 take away 5? 7. There you go. So when you divide f of x by h of x, you will get a remainder of 7. So is h of x a factor of f of x? You think, Layla?
No.
No. H of x is not a factor. So if you were trying to factor it, x minus 3 is not what you should use. All right. Let's do f of x divided by g of x. Okay. In this case, are we dividing by something you can use the remainder theorem on? Yeah?
Yeah.
Yeah, we still are. But we gotta rethink this bottom a little bit. Okay, we gotta think of it as x minus, and we need to know what the number in that box would be. That's what's going to get plugged in. So how would we rewrite the bottom so it's of the form x minus a number? Yep.
X minus -1.
Right. Now, -1 is the number you are plugging in. Okay. If you plug in +1, no, it's wrong. Okay, you're plugging in the number after the minus sign. Okay, so let's plug in -1. Okay, so we got -1 cubed minus 2 times -1 squared. Minus 1 minus 5. Okay, so that's going to give me -1. -1 squared is 1. 1 times -2 is -2. -1 minus 2 is how much? -3 minus 1 more. And minus 5 more. Negative how much?
-4 minus 5.
Yeah.
-9.
-9. Okay, so we got a remainder of -9. Is g of x a factor of f of x? Declan?
No.
No, not a factor. So what is a factor? Well, we don't want to just keep guessing. Let's try x minus 3, x minus 2, x minus 5. You know, there is a way to figure out what is a factor, but that's not today. But those two are not. All right. Actually, I'm not worried about that right now, I don't think. Okay, so let's look at this one. So this one says use the factor, or we're just going to say remainder theorem. It's basically the same thing. Use the remainder theorem to show that x plus 2 is a factor of that. So what are we hoping happens if they're telling us to use the remainder theorem to show that is a factor of that? Yeah?
Remainder of 0.
Right. We're going to hope when we divide them, we get a remainder of 0. Okay. First of all, do we have to do this with long division, or can we apply the remainder theorem? Yeah, myself.
Use the theorem.
Yep, we can use the theorem. we got to know what number we would be plugging in for x in the top. What number would we be plugging in? Yep.
-2.
-2. Okay, think of this as x minus -2. So let's plug -2 in for x. And because of that theorem we went through, plugging in -2 will automatically give you the remainder. And we proved why that works. What's -2 cubed? -2 cubed gives me, yep,
-8.
-8. And then -2 squared is 4 times 5 is 20. 5 times -2 is -10, minus 2. -8 plus 20, that gives me -12. I'm sorry, positive 12. Minus 10 minus 2. What's 12 minus 10 minus 2? 0. That means that x plus 2 is a factor of that cubic. So now you could do something like this. X cubed plus 5x squared plus 5x minus 2 equals, and now I could ask you to factor that. We already know x plus 2 is a factor. How would you get the other factor? Yeah.
Would you have to divide what that take to?
Would you say that again?
Would you have to divide like x cubed plus 5x squared plus 5x minus 2 by x plus 2, or would that take 2?
No, you'd have to divide it. Yep. So yeah, you would divide it, and then how would that give me my other factor?
It would be your quotient.
It would be my quotient, exactly. So just like if I told you I want you to factor the number 20, 5 is a factor. How do you get the other one? You got to take 20 and divide by the factor that you know. Well, same thing. Take this, divide by the factor that you know, kind of like moving it to the other side, and you can solve for the other factor. And when you divide by x plus 2, that is going to turn into a quadratic. So the other factor here, when you divide this by this, your quotient will be a quadratic, which if we had to solve it, now we've got the exponent of 3 down to an exponent of 2. But it's only because we figured this out. Okay? So how would you have gotten that x plus 2 to start with? Well, we'll look at that tomorrow. Okay. Any question on that one? All right, so let's look at this. So these are all equivalent statements about roots and zeros. So let's say that you have a number that is a solution to the equation f of x equals 0. So pretend like it's something like 2x plus 6 equals 12. If you were to solve that, what would you get for x? You know what, actually, I said 0. So let me change it to actually being 0. Just change it a little bit. What would you get for x now? Yep. -3. So -3 is a solution to that equation. Everybody agree with that? Okay. -3 is also called a what? Yeah? A root? What else is -3 called? Yeah?
X-intercept?
It's an x-intercept. One other thing it's called. Yeah?
0.
A 0. All those things are true. I think you said them all. So -3 is a 0. -3 is a root. Negative 3 is an x-intercept. This is the one that's most important, though, right here. If negative 3 is a root, so think about that. If negative 3 is a root, then that would automatically mean something has to be a factor, right? Think about negative 3. If you plug that number in and you get 0. Okay. We talked about what happens when you plug a number in and get 0, and that gives you the remainder. So we're getting a remainder of 0 when you plug negative 3 in, right there. What would have to be in the bottom of this problem for you to be plugging in a negative 3 to check for the remainder? What would you be dividing by in the bottom? Yeah?
Would it be x plus 3?
Yeah. If you were dividing by x plus 3, and you wanted to check the remainder, you would be taking negative 3, which happens to be the root, and plugging it in and seeing if you get 0. So when you plug in negative 3 here, it does give you 0. So that means this would have to be a factor, because you're getting a remainder of 0 when you plug negative 3 in for x. So when you know that a number is a root, you automatically know that x minus that number has to be a factor. Okay, it has to be. Because you're plugging it in and you're getting 0. That's essentially your remainder. Okay. So what I'm going to have you do now is I'm going to give you roots to a problem, and I want you to work backwards and tell me what the problem must have been that had those roots. As long as you understand this concept, that's all we need to know. Okay. Any questions on that? So I want you to find a polynomial that's degree 3, so cubic. It's all real roots, no imaginary. And the roots are negative 2, 1, and 3. Okay, so I'm basically looking for what would be in the top in that box right there. Okay, let's start with the negative 2. You need to give me something in this box that if you plug negative 2 into it, it would come out to an answer of 0. Now remember, if you plug in a number and you get a 0, that would be your remainder 0. What would you have to divide by if you were plugging in negative 2 into the top to check if this was a factor? Yeah?
X plus 2.
Right. You would have to make sure that x plus 2 was one of the factors. Right? So that's one of them, okay, x plus 2. What would be another factor that you would be checking for? Yeah?
X minus 1.
Right. I need to figure out a formula in this box that I can plug 1 into and get 0. Okay? That's what it means to be a 0. You plug in that number, the answer comes out to 0. When would I be plugging in a number 1 in the top? Well, if I had a factor of x minus 1 in the bottom, that's how I would check if that was a factor of the top. So I'm forcing it to be a factor. Right? And I would need one more. What would be my last factor? Yep.
X minus 3.
It would have to be x minus 3. I need to come up with a polynomial that I can plug 3 into, and I know it will come out to 0. This polynomial right here will do that. If I plug in 3 here, I get 0. If I plug in 1 here, I get 0. And if I plug in negative 2 there, I will get 0. So now I just need to multiply that out to get my final answer. Okay, so that's going to give me x squared. Let's see, that's going to give you minus x plus 2x minus 2. And then multiply one more time. So x cubed, x squared, minus 2x, minus 3x squared, minus 3x plus 6. And now combine it all together. So x cubed, x squared minus 3x squared, negative 2x minus 3x, and plus 6. There you go. So if I graph that, it should cross the x-axis at exactly the 3 numbers that they wanted me to. Well, let's see. So we've got x cubed minus 2x squared minus 5x plus 6. So remember, we're looking for negative 2, positive 1, positive 3. And let me do zoom 6. Negative 2, positive 1, positive 3. Perfect. That's exactly where I wanted it to cross through. So any question on how, if I give you a root, you can turn that into a factor to multiply together to get your formula. And you can do that for as many roots as you want. If you wanted it to pass through more roots, just do x minus every root you want it to pass through. And those are your factors. Okay. So let's try a couple, we'll finish up. This is the reverse now. I'm not asking you to come up with an equation. I'm giving you the equation. I want you to tell me the roots. Okay. And they give you a hint on the first one to use factor by grouping. What can you factor out of the first 2 terms? Yep.
X squared.
Yep. And what would that leave you with if you factor out the x squared?
X plus 2.
Yep. X plus 2. What can you factor out of the last 2 terms? Yep. Factor out a negative 4. And what would that leave you with if you factor out a negative 4? It'll leave you with another x plus 2. That's how factor by grouping has to work. So now, what do that and that both have in common as a factor? Yep.
X plus 2.
So now we're going to factor that out. If you factor out the x plus 2 from the first term, what's left? Yep. X squared. And if you factor it out of the second term, you're left with a minus 4. And x squared minus 4 factors again. How does x squared minus 4 factor? Yep.
X plus 2, x minus 2.
Yep, x plus 2, x minus 2. So you've worked all the way backwards to basically the step that we started at in the last problem. Okay, so it's the last problem in reverse. Now, I just need you to tell me the roots. If the same root occurs more than once, you don't need to tell me it occurs twice. Okay? So what are all the roots in this problem? Just give me distinct answers. Yep.
Negative 2 and 3.
Negative 2 and 2. Negative 2 does occur twice. That's called a repeated root. Generally, when you have a repeated root, the only way it can do that is if it comes up to the axis, bounces away from it, and goes like that. That's how you can only get 2 answers when you have a cubic. It has to bounce off it. If it goes through it, then you're going to get 3 answers. Right? It's going to go through, come back, and go through again. Okay. Any question on that? Okay. And the last one, they're suggesting to use the graphing calculator, which means factor by grouping probably would not work on this one. It's a cubic, so how many times could it cross the x-axis at most? Nick?
3.
Could cross 3. How many times could it cross the x-axis at a minimum? Yeah?
Once.
Why does it always have to cross at least once? Not sure. Why once? Why not none? Parabola can have none. Yeah.
The end condition for a cubic equation has to have a positive and negative.
Okay, so one end goes up, one end goes down, and what else do we know about cubics? Something very important. Just because one end goes up and one end goes down does not guarantee it's going to cross the x-axis. Yeah?
Would it be that it turns twice?
Well, that would have to do with the maximum number of answers you could get. But we're looking to prove why it has to cross at least once, yeah?
Continuous.
It's continuous, right? If you go up forever and down forever and you never lift your pencil while doing it, you will cross the axis at least once. So you could get 1, 2, or 3 solutions that are real. Imaginary, that's a whole different thing we'll talk about later. Okay. And in this case, we only get 1 real solution. Looks like it's at 2, but never just write it down by looking at the graph. Always check it, because it could be like 1.97 or something. Okay, so go left, right, guess. But this one was exactly 2. Right? You never know. So just always check it. Okay, and now that we know that's 2, and we know that it's the only real root, technically this does have to have 3 answers. That means the other 2 answers are not real. They are imaginary. So you always have to have as many answers as the exponent that you have. Sometimes answers can be repeated, like in the last problem we did. Sometimes answers can be imaginary. But there does have to be 3 answers. Okay? But we're only going to worry about the real one for now. Okay, so x equals 2. Okay, any question on that one? All right. So that's homework for tonight. Actually, I think I can change that. It's 9 through 9, 11. It's just, I'll just let you write it that way. I could probably write it as like 9 through 19 odd, and then 20 and 21. Okay, so those are the questions on 171. Tomorrow we will finish our material for the week with 3-4. We're going to look at another way to do division besides long division. It's actually a faster way called synthetic. We'll look at that tomorrow.